Okay, we are back with the new lecture. We started chapter 3. We define some notations and terminology. We define order of a group. We define order of an element. We gave some examples about it, and then we define the subgroups. Now we will talk about the subgroup test. How we are actually checking whether a subset is a subgroup of a set of a group or not. The topic would be subgroup test. When determining whether or not a subset H of a group G is a subgroup of G, one need not directly verify the group axioms, but the next three results provide simple tests that suffice to show that a subset of a group is a subgroup. Okay, and those we define with in theorem. So our first theorem is going to be theorem 3.1, which is about one step subgroup test. Okay, perfect. The statement is, we say let G be a group and H a non-empty subset of G if AB inverse is in H, if AB inverse is in H, whenever A and B are in H, then H is a subgroup of G. Now, in additive notation, we say if A minus B is in H, whenever A and B are in H, then H is a subgroup of G. Okay, so this is the statement, and we can actually prove this statement. Now, group theory proofs are very easy and straightforward proofs. You just need to follow the arguments, and you are good to go. So don't be scared of those proofs. Okay. Remember what we needed to do? We needed to prove that AB inverse is in H whenever A and B are in H. Then H is a subgroup. Or in addition, If A minus B is in H, then whenever A and B are in H, then H is a subgroup, right? This is the proof. Now, since the operation of H is same as the operation of G, it is clear that the operation is associative. Now, the idea of the proof is to show that H contains all of the properties of G, okay? And it is itself a group. So we begin with and say that since the H is the same as the as that set of G, it is clear that this operation is associative because G is a group, so it should have associative operation. Next, we show that identity is in H. Now, since H is non-empty, we pick some element. So we pick some X in H, right? And then letting A is X and B is X in the hypothesis, we have E is equals to X inverse, which is nothing but A B inverse is in H. Now to verify that X inverse is in H, to verify that X inverse is in H, all we need to do is to choose A is equals to E and B is equals to X in the same statement of the theorem. Theorem. Now finally, the proof will be complete when we show that H is closed. And that is if x comma y belongs to H, we must show that xy is in H also. Well, we have already shown that y inverse is in H whenever y is in H by the above argument in H. So letting A is equals to X and B is equals to Y inverse, we have we have X Y is equals to X Y inverse whole inverse, and that is a B inverse is in H. So what we did actually, we said that the operation is associative, then we said that the identity lies in H, then we said that for an element in for an element in H there is exist an inverse for that element in H, and then we in the end we said that H, the operation of H is actually closed by assuming an element and by assuming two elements, and we said that their product is also in H, and that makes H a group. And if H is a group under the same operation of G, then it is a subgroup because it is a subset. So all you need to check that H is a subgroup, you need to check that AB inverse is in H for some elements A and B in H. That's it. Okay, this is a one step subgroup test, right? Perfect. Now let's talk about it. So we are saying, although we have dubbed theorem 3.1 the one step subgroup test, there are actually four steps involved in applying the theorem. Notice the similarity between the last three steps between a list below and the three steps involved in the second principle of mathematical induction. Number one is, first you need to identify the property that distinguished the elements of H, that is, identify a defining condition. Two, we need to prove that the identity has property P. This verifies that H is non-empty. Three, we need to assume that two elements A and B have the property P. Four, we use the assumption that A and B have the property P to show that AB inverse has the property P. And that property is something which distinguishes the elements of H. Okay? And let's try to illustrate this thing by an example. So example says And we consider this example 4 because we have already presented 3. Example 4 says, let G be a group, G be an abelian group with identity. Let G be an abelian group with identity E. Then we write H as X from G such that X square is E, is a subgroup of G. Here, the defining property of H is, here, the defining property of H is the condition X square is E. So we first note that E square is E. Now E square is E. So H is non-empty. Now we assume that A and B belongs to H. Assume A comma B are coming from H. This means that A square is E comma B square is E. Then finally we must show that AB inverse square is E. Since G is abelian, we can say that AB inverse square is A B inverse A B inverse, and that can be written as A square B inverse B B inverse square, or you can write it A square B square inverse. And this is nothing but E into E inverse, which is nothing but E. Therefore, A B inverse belongs to H. Right. Therefore, AB inverse belongs to H. And by one step subgroup test, H is a subgroup. H is a subgroup of G. Okay. Now, in many instances, a subgroup will consist of all elements that have a particular form. Then the property P is that the elements have that particular form. And let's illustrate that with an example 5. Let's say that let G be an abelian group under multiplication with identity E. Then H is a subgroup. H is a set which contains X square, where X is coming from G, is a subgroup of G. In other words, H is the set of all squares. Now, since E square is E, so identity has the correct form, right? Next, we write two elements of H in the correct form. Now, writing elements in the correct form is what we have mentioned previously. So we write two elements of H in the correct form, say A square and B square. And A comma B in H. Now, now we must show that A square B square inverse is in correct form, right? That is actually that A square B square minus 1 is the square of some element, is the square of some element. Since G is abelian, we may write A square B square inverse is AB inverse square, which is the correct one. So AB inverse is in H. Thus, H is a subgroup of G. Now, we give another theorem and we call it two-step subgroup test. So let's write the theorem. Two-step subgroup test. Okay. The statement says let G be a group and let H be a non-empty subset of G if AB is in H whenever A and B are in H, means H is closed Under operation, operation, and A inverse is in H whenever A is in H. Means H is closed under taking inverses. Then H is a subgroup of G. Okay? Proof. Now, since H is non-empty, the operation of H is associative. The operation of H is associative. H is closed. H is closed. And every element has an inverse. Right? In H. Now, all that remains to show is that E identity is in H. Now, to this end, is an let A belongs to H, then A inverse belongs to H, and A into A inverse is going to be E are also in H. That's it. This is the proof. Now let's illustrate. So when applying the two-step subgroup test, we proceed exactly as in the case of one-step subgroup test, except we use the assumption that A and B have the property P to prove that AB has the property P and that A inverse has the property P. Okay, so those are the assumptions. Now let's present the example. Example, we call it 6. We say that let let G be an abelian group and then H is equals to X from G, given that order of X is finite. is a subgroup of G. Okay. Now, since e power 1 is 1, H is non-empty. To apply the two-step subgroup test, we assume that A and B are in H and prove that AB is in H. Prove that AB is in H and A inverse belongs to H. Okay. Now let order of A is M and order of B is N. Then, because G is abelian, we have because G is abelian, we have AB power Mn, AB power Mn is equals to A power M power N, B power N power M, and this is equals to E power N, E power M, which is equals to E. Thus, AB has a finite order. Thus, AB has a finite order. This shows that order of AB is Mn, order of AB is Mn, right? Moreover, A inverse power M is going to be A power M inverse, which is going to be E power E inverse, which is E. So this shows that A inverse has finite order. Perfect. Now we next illustrate how to use the two-step subgroup test by introducing an important technique for creating new subgroups of abelian subgroups from existing ones. The method will be extended to some subgroups of non-abelian subgroups in later chapters. Okay, perfect. So let's try to do that by using an example. So example 7. Example 7 says let G be an abelian group and H and K be subgroups. Then HK is a set which is HK, given that H is from H and K is from K, is a subgroup of C. First, note that E is nothing but E into E belongs to HK because E is in both H and K. Now, suppose that A and B, A comma B, are in HK, then by definition of H, there are elements H. There are elements H1, H2 in H and K1, K2 in K, such that A is H1 K1 and B is H2 K2. We must prove that AB is in H and A inverse is in HK. A inverse is in HK. Now observe that because G is abelian, and H and K are subgroups of G. Of G, we have we have AB is equals to H1 K1 H2 K2, and that we can write H1 H2 K1 K2 belongs to H. Okay. Likewise, we write A inverse is equals to H1 K1 inverse. We write it K1 inverse, H1 inverse, but we have the abelian property, so we write it H1 inverse, K1 inverse, and this belongs to H. That's it. Now, how do you prove? Okay. Now, another thing is, how do you prove that a subset of a group is not a subgroup? There are three possible ways, any one of which guarantees that that the subset is not a subgroup. The question is, how do you prove a subset is not a subgroup? Answer is 1. Show that E does not, let's write it in the words, show that the identity is not in the set. Okay. 2. Exhibit an element of the set whose inverse is not in the set. Exhibit an element of the set whose inverse is not in the set. 3. 3. Exhibit two elements of the set whose product is not in the set. Perfect. Now let's do an example. We say let G be the group of non-zero real numbers under multiplication. G be a group of non-zero real numbers under multiplication. So we can write G is, because we are a grown-up people now, so we write R star under multiplication. This is G, and our H is a set which is contains elements from G, given that the element X is 1 or X is irrational. And the set K contains elements from G which have the property that they are greater than or equal to 1. Then H is not a subgroup of G. Then H is not a subgroup of G, since under root 2 belongs to H, but the product is 2 does not belong to H. Also, A is not a subgroup of G, since 2 belongs to K. but 2 inverse does not belongs to, and that's it. Now, when dealing with finite groups, it is easier to use the following subgroup test. Which one? The one we will present now in the form of theorem. So, theorem 3.3, which we call finite subgroup test. And the statement is, let H be a non-empty finite subset of a group G if H is closed under the operation of G, then H is a subgroup of G. Now, this is a very strong thing. You just need to check the closedness if you have a finite subset, finite group, and finite subset. So let's prove this. So we say that in view of theorem 3.2, we need only to prove that A inverse belongs to H. A inverse belongs to H whenever A belongs to H. So if A is the identity, then A inverse is also equals to A. Sorry, I got the back. A inverse is also equals to A, and we are done. But this is not the case only. If A is not the identity, so we consider the sequence A, A square, and so on. By closure, all of these elements belongs to H, right? Now, since H is finite, not all of these elements or distant. Say a power I is a power j and I is greater than j, then a power I minus j is nothing but e. And since a was not e, I minus j is actually equal to greater than 1. And thus, a into a power I minus j minus 1 is going to be a power I minus j, which is equal to e. And therefore, therefore, a power I minus j minus 1 is equals to a inverse. But I minus j minus 1 is actually greater than or equal to 1, implies a power I minus j minus 1 is inside H. And we are done. And we have proved that A inverse is in H. And here we will end this part of the lecture. So thank you so much. Have a good day. Have a nice learning group theory. And I'll see you in the next lecture where I will define examples of subgroups. Thank you.